So any question before we start? Okay. On Sunday we didn't do anything. Okay, so today we will be starting a new subject, scattering. Well, this is probably the most important subject in all of physics. So basically all the experiments we do is some kind of a scattering. That's how we understand the nature, how we learn something about the nature. And the basic idea would be, we will first, let's start with the classical description of scattering. It's more intuitive. And then we will be translating it to the quantum mechanical description and see what we can do about the scattering processes in quantum mechanics. Now, in classically, what we will imagine is, so we have something over here, which we don't know. We would like to make observations about it. We would like to see what its properties are. So what we do is we just send some particles. It can be photons, for example. That is basically how we see an object. There is something that sends photons to an object, and the object scatters some of the photons. And once it is scattered in a given direction, if our eye or the detector is in that direction, we will be observing the object, and hence we will say that there's something over there in that region. Now, to describe the scattering processes, basically what we do is we will be defining some differential cross-section. Well, whether the particle is coming from this point or from this point, it doesn't really make any difference. The important thing is that as long as the particle is aimed in an area, something like this, any particle that is aimed within that area, perpendicular to that area, will be scattered in a direction given by this cone. And basically this cone will be describing, this direction described by this cone, we will be describing using what's called the solid angle. So if any object is within this area is what we call the cross-section, differential cross-section. Anything that is scattered in that d sigma, anything that is targeted within this area will be scattered into the solid angle given by omega, d omega. And eventually our aim would be to calculate d sigma over d omega. And if we are interested in let's say the total cross-section of the object, so basically we should be counting all the area, summing all the area in which if an object goes to that area, it will be scattered by some angle. So that's kind of the total cross-section. Now, this is the definition of the cross-sectional area. Classically, this is easy to describe, to define, but even classically, it's not so easy to measure because, especially if you are interested in subatomic particles or electrons, let's say, you cannot really, and also in quantum mechanics, you cannot really target an object at a very small area. That's against the uncertainty principle. So this definition, although it's true, it will not be so much of a use for us. Now, in practice, what we do is we just send a beam of particles. So there is an incident flux of particles. So J in is the incident flux of particles. Well, that is basically the number of particles passing through a unit area per second. This is what we mean by the flux of particles. And here is our scattering source. There's a target over there which we are aiming at. Now, of course, all these particles will be, some of them might be scattered, some of them might miss the target. But if you put a detector over here, it will only be measuring the scattered particles. Let's say the JSC to be the flux of scattered particles. And then our detector per unit second, it will be measuring some number of particles. Let's say the n is the number of particles measured by the detector per second. Let's also make a few more definitions. This is the RD is the distance of the detector. A, let's say dA is the area of the detector. So basically, our detector will measure all the particles that is scattered into a solid angle given by dA over RD squared. This is the solid angle that the detector measures. Let's assume that the total area of the beam, let's call it A. And we know that the particles that hit the sigma area will be scattered into my detector. So what fraction of the particles will be hitting that dA? Huh? D sigma, sorry. D sigma over A. This is the the fraction of particles that will hit the area the sigma and scatter into the solid angle d omega. So dN, this is the number of particles per second observed by the detector, will be the total number of particles per second. Well, that is J incident times A. This is the total number of particles that is arriving the scattering center per second. And among these, the sigma by A will be scattered into my detector. Well, basically we are done in the definition of the d sigma. Now we can furthermore say that the n will be actually nothing but J scattered. This is the scattered current in the direction of my detector at the point of my detector times RD squared d omega. And so the sigma will be nothing but the scattered current times RD squared divided by J incident times d omega. Now, this is what we had done. We were studying the scattering process. We first defined what we will be meaning by scattering cross-section. We said that if we have, let's say, a scattering target somewhere over here, we will be sending our particles, and if our particles are aimed within this area, the sigma, they will be scattered into a solid angle described by this d omega. So that is how we define the cross-section. scattering cross-section or differential cross-section. It is the actual area, physical area, that if you can aim your target within that area, it will be scattered in your detector. Now this is intuitive, it's nice, but nevertheless this is not practical, because even classically, if you work with very small particles, you cannot really aim them at a given point. In quantum mechanics, it's even in principle not possible. So what we do is we just send a beam of particles with an initial flux, let's call them J in. They are then scattered off our source, and then we define the so the sigma over A. If the total area of this our beam is A, only d sigma over A of them, that fraction will be hitting my d sigma, and hence scatter into my detector. So the total number of particles observed by my detector will be the incident number of particles, the number of particles per second, dn. That my detector will observe will be the number of particles incident in my target per second, multiplied by the fraction that will be scattered into my detector. Now, furthermore, we can say the number of particles observed by my detector will be nothing but the current density of particles at the point of my detector times the area of my detector. The area of my detector is nothing but the distance of the detector from my source times the solid angle corresponding to my detector. So if you just use these two equations over here, you can express the solid angle in terms of the currents of particles. Now, it seems that it depends on the distance squared of the detector. So the further away my detector is, it seems as the d sigma will be larger. But that's not true. Just keep in mind that J scattered current density will be proportional to 1 over RD squared. So the product J scattered multiplied by the distance of the detector squared will be a constant. It will not depend on the position of my detector. And if you look at this, the particle current we can define also in quantum mechanics, or classically, the incident current is easy to choose a given incident current. You just send a bunch of particles in a given direction. That creates an incident current. You can measure it. You don't need to aim any particle in any very small area. The only thing you need to do is, here is your scattering. If this is your scattering, send your bunch of particles in this direction, put a detector somewhere over here, and you are done. Just measure the flux of particles. Now, the next thing is, okay, so this is fine. How do we do it in quantum mechanics? How do we describe the particle flux? Do you remember particle flux in quantum mechanics? Something like that. Let's derive it. You see, psi star psi. This is the probability density. Or if you normalize it to n particles, let's say, in that case, n particles in the same state, you can also treat this as the number density of particles. Now, if you assume any volume, if the number density within this volume is changing, it will be due to the flux of particles leaving this region. So you can just say that within this volume, the integral of psi star psi, c cubed r, the rate of change of this if there is a positive flux, if there is a flux going out of my volume, this number should be decreasing. This will be equal to minus J dot ds over the boundary of my volume. So this is how we can identify the particle current described by a wave function. Now let's just do the algebra. So the derivative is just del psi star by del t, psi plus psi star del psi by del t, d cubed r. This is equal to minus this is equal to v, let's see, plus I h bar del psi by del t complex conjugate times 1 over minus I h bar psi plus psi star I h bar del psi by del t 1 over I h bar d cubed r. And this is nothing but using our time dependent Schrödinger equation. This is h psi, and so is this one. H psi complex conjugate times psi, that's I over h bar minus psi star h psi d cubed r. I will assume that h is equal to minus h bar squared over 2m Laplacian plus v. Now v is real. Everything is in fact real in this Hamiltonian. V is real, and so v in both of these terms, they just cancel. And what we are left with is, let me take this minus h bar squared over 2m also out. Laplacian of psi star times psi minus psi star times the Laplacian of psi d cubed r. We are almost done. This is equal to minus I h bar over 2m v. What is left inside, I can write it as the gradient of psi star psi minus, this is Laplacian, psi star gradient of psi d cubed r. Now if you just calculate this outermost gradient, you get you get mixed terms which involve the gradients of both of the wave functions, both psi and psi star, but due to the minus sign in between, they just cancel, and we are left with the previous line. But now there is a vector field over here. We are taking its gradient and integrating over a volume, and instead of that, we can just write it as a surface integral. This is equal to I minus I h bar over 2m over the boundary of v, gradient of psi star psi minus psi star gradient of psi ds over the area. And this should be equal to minus j dot ds. And so we know the particle current described by any wave function. J is equal to I h bar over 2m gradient of psi star psi minus psi star gradient of psi. Now let's do a simple example. Let's look at the plane wave. What's the wave function of a plane wave? with momentum, let's say P. P dot R over H bar. Well, the gradient of psi, this is just I P over H bar times psi. So if we just put it above, J will be equal to I H bar over 2m. Gradient of psi star, it will be minus I P over H bar. Psi star psi is just 1. Minus gradient of psi is just I P over H bar. Again, psi star psi is just 1. This is equal to I H bar over 2m minus 2I P over H bar. H bars cancel, 2's cancel, I times minus I just gives 1. And so the current density is P over M. Times the velocity. Well, that is what we would have expected. The current density should be proportional to the velocity of the particle. But of course, we haven't properly normalized things, so we cannot really say that this is neither the this is not the particle per unit area per second. Up to a normalization, this is the current. Now, what we will be doing is basically this one. Now we know the current also, how we can describe, how we can talk about the particle current. And furthermore, in the definition of this cross-section, how we normalize the currents will not be that important because it's just the ratio of the current densities. Well, this is what we will do. We have an incident particles that we can use plane waves to describe them. There's the incident particles, and then there's the scattered particles, which are very far away from the potential. So let's see. How will the wave function look very far away from the potential? So let's first study them. Now we know the Hamiltonian. We are looking for the solution of this one. At a given energy, we are basically looking for solutions of this one, which will be describing our scattering state. So we should be looking for the solutions and the boundary conditions that we want to impose is that in this, let's say this is my potential. If you go very far away here, it should be just plane waves. That's your boundary condition. That will represent your incident particle. And if you look, let's say at this point, very far away, it will be some particle that is moving away from this center. Those are the solutions that we are looking for. Now, very far away, the potential V of R will be 0. We can look for a solution in the form, let's say U over R times YLM. We can look for such solutions. And the equation satisfied by this U of R will be just minus H bar squared over 2m d squared U by dr squared. This should be equal to, well, we can also add the, let's look at L equal to 0 first. It will be simple. Well, in fact, we can even keep the L term. Plus L plus 1 over R squared with some coefficients that depends on H bar squared and 2m, etc. This should be equal to E times psi. But remember, we are looking for a solution that is very far away from the potential. So R is large. If R is large, Oops, these are U's. If R is large, this is negligible. So at the very far away, our solution should look like this one. It should satisfy this equation. And if we define k to be square root of 2me, or h bar k to be 2me, what we have will be just u is equal to a times e to power I kr plus b times e to power minus I kr. But you see, the first solution, but both are spherical waves. They depend only on the distance. But the first wave is a wave that moves to larger values of a. This is the outgoing wave. Whereas the first one, the second one, will be just a wave that goes towards smaller r. So that's what we call the ingoing wave. So we have these two solutions, and we know our boundary conditions. We are looking for a wave that will have a plane wave on one side, and at some other angle it should look like an outgoing wave, because that's what the particles are doing. We have particles coming, they are scattering from a scattering center, and then they will be moving away from the scattering source. So we should be having this outgoing wave solution is the solution that we are looking for. Now this is the limiting form of my wave. Let me write my wave at a point very far away from my scattering center. I can have some normalization. There will be a plane wave part. This is the incident wave that I'm sending. Plus, there will be an outgoing spherical wave. It will be e to power I kr over r times some number. Of course, that number can depend on the angles. But the radial dependence is kind of fixed at a very far away point. So this is how my scattering wave function looks like. Now, of course, what I don't know what f is, and that the explicit form of f will depend on the potential. And in a sense, the rest of the scattering discussion will be concentrated on how can we calculate this f. But at least whatever the potential is at a faraway point from my scattering source, this is how my wave function should look like. Now, we had already calculated the incident current density. This is the incident wave. And this is the scattered wave. We already know the incident current density, which just turned out to be, well, if you put a normalization, a squared times k, h bar k over m. H bar k is the momentum divided by m, that's the velocity. This is the incident current density. Now we need to calculate the scattered current density. Well, we already know the wave function, the scattered wave function. So just use this expression. Now we need to know the expression of the gradient, where the gradient of any function will be nothing but 1 over the derivative of the wave function with respect to r times in the r hat direction plus 1 over r times some operator acting that depends on theta and phi acting on psi. I don't care what that operator will be. It will not be important for me. Because you see, eventually what I will need to do is I need J scattered times RD squared, the distance of my detector squared. But then assume that the detector is very, very far away. For example, if you imagine the scatterings that we study in LHC, the particles are interacting at distances of the order of 10 to the power minus 8, minus 9 meters. Whereas the nearest detector is further than 1 millimeter. So the distance of the detector is practically really infinite, almost infinite. Now if we take this limit though, you see the scattered wave already has this 1 over r dependence. If you multiply two of them, you get a 1 over r squared already, only because of the wave functions themselves. Now if you have these terms over here, they have an additional 1 over r. Well, that makes 1 over rd cubed. If you multiply it with rd squared, it just goes to 0. In the far zone, or in electromagnetic terminology, in the radiation zone, these terms do not contribute to the current. Now, furthermore, if we just take the derivative of this 1 over r, again, we don't really care about them, because the derivative of 1 over r will just bring some 1 over r squared, and again, at the far distance, in the radiation zone, in the electromagnetic terminology, they will not contribute. So the only thing that will contribute here into this derivative, psi scattered, will be basically the exponent. So the gradient of the scattered wave function is just a times I times k times e to the power I k r over r plus, in the r hat direction, plus terms that are of the order of 1 over r squared, which I don't care. So let's say the current, then the scattered current is just I h power over 2m minus I k, because here we have the complex conjugate. In the first term, we are taking the gradient of the complex conjugate, psi scattered squared minus just ik in the r hat direction times psi scattered squared, again in the r hat direction. And again, this just gives us just h bar k over m. Psi squared is a squared times f theta and phi squared. And that's it, in the r hat direction. This is the scattered current. But you see, if you look at this expression is nothing but, at least the magnitudes, J scattered is nothing but J incident times f theta and phi squared, 1 over r squared, times 1 over r squared. Yes. The scattered wave function is proportional to 1 over r, so that's why I have that 1 over r squared. Plus, of course, terms of the order of 1 over r cubed. So basically we are done. r squared times j scattered over j in is equal to f theta and phi squared. And as I had said before, the normalization is not important, so that's why we ignored it. And so basically, if you can calculate the wave function at an arbitrary point and take the limit of large R, and if you just can show that this is equal to some number, normalization constant, e to power I k dot R plus f e to power I kr over R, then the scattering cross-section, d sigma by d omega, is just equal to that number, theta and phi squared. And this is basically how we will be calculating the scattering cross-section in quantum mechanics. Any questions?
Wave function, how are we going to extract the wave function?
Well, that is something we will start to do on Friday.
On slide 3, at the end of it, this one, in the L, when you said this is negligible, but you said the constant next to the L plus 1 is 1 over R squared. Sorry, it is proportional to R squared.
Okay.
So R squared, 1 over R squared, it's not negligible.
The coefficient over here?
Yeah.
No, I mean, that coefficient is h bar squared over 2m.
No, because I heard R squared. Okay.
Minus h bar squared over 2m. There's no r. Now let's do a simple example. In classical mechanics, in classical scattering cross-section. And then Friday or on Sunday we will be doing the quantum mechanical analog. Now let's just assume that we have a hard sphere. What is the scattering cross-section? Differential cross-section. So let's see how we define the scattering cross-section. So if you just send a particle in this direction, let's say this is the center. If you imagine this line going through the center parallel to our incident direction, this is B. B is called the impact parameter. Now we know that if this is a hard sphere, it will just reflect like the light ray. So the incident angle will be equal to the reflected angle. So if this is theta, it will scatter in this direction, where this is also theta. Let's call this angle chi, and this is our scattering angle. So initially this was the direction of our particle, and after the scattering this is the direction, so this is how much it changed its propagation direction. That's how we define the scattering angle. So from a far away distance, this will be our point object. So we send it over here, and then it will be scattered in this direction. This is chi. Now, what else do we know if, let's say, instead of B, we send it at a distance B plus dB, then chi will change from chi to chi plus B chi. Chi angle will also change slightly. Now, we can also relate this angle chi and B. Let's say this is our angle theta. So theta is nothing but pi minus chi over 2. pi over 2 minus chi over 2. And from this right triangle over there, we know that sine of theta is equal to b over r, or b is equal to r times sine theta, r times sine pi over 2 minus chi over 2, or b is equal to r times cosine chi over 2. dB will be equal to minus r over 2 sine chi over 2 times d chi, how the scattering angle changes by the impact parameter. Now, what do we know? If b is fixed, we know that for a given b, if you know b, you know chi. B fixes the scattering direction. Now, rather than looking at from the side, let's just look at it from where we send the particle. So as long as the particle hits this region, this circular region of thickness dB and radius b, it will be scattered by an angle r, by an angle chi, that we know. Now, furthermore, we want to define it, the sigma, to be the area at which if it will scatter not just a chi. You see, if this is our scattering, this is scattering by a chi, this is also scattering by chi. We would like to fix the solid angle. So we also would like to fix the phi. So if you send it in this region, let's say the phi, if you send it within this area, then it will scatter into a solid angle described by a chi and phi. Do you agree? So let's say then the sigma is nothing but, this is b. So this side is b d phi. So the sigma is nothing but b times d phi times dB. But we already know what dB is and b is. Now b is r times cosine chi over 2. This is b. Well, let's just keep d phi. dB is r over 2 sine chi over 2 d chi. Well, that minus sign, I just ignored it because it only tells me that if I increase b, then the scattering angle decreases. So that's not really what I meant. This solid, this differential cross-section is an area which is defined to be a positive number.
D sigma dediğimiz şey bizim particle velocity'mize tam dik durmuyor galiba.
No, it should be perpendicular.
Should it be?
Yeah. No, you see, here I'm sending the particles perpendicular to the screen. And the sigma is in the screen. So it's perpendicular to the velocity vector.
Sphere, from the curvature of the sphere, you mean?
No, you see, my sphere is over here.
That's the part.
This is my sphere. So if we just look at it again from the side, this is my sphere that I'm targeting. And this is my ring. This is B. dB is this thickness. Yeah. The ring over there is not on the sphere. I'm just looking at this. So this is my two-dimensional view. I'm targeting an area in this two-dimensional view. Okay, so let's come back over here. This is r squared over 2, r squared over 4, sine of chi, d chi, d phi. But this is nothing but my solid angle. This is how I define the solid angle. So the sigma over the omega is equal to r squared over 4. This is the cross-section is constant in this example. Now, furthermore, if we calculate the total cross-section, this is nothing but the sigma over d omega, multiply by d omega, integrate over all omega. The sigma over d omega is nothing but r squared over 4, that is constant d omega. Well, this is nothing but 4 pi, the total solid angle. So we obtain pi r squared. This is nothing but the geometrical cross-section of my sphere. That's kind of expected because if I target any object in that area, they will scatter. And if I target them out of that area, they will not scatter. That's what this total solid angle measures. A sophisticated way of obtaining the area of a circle, of a disk. Now, any questions?
Can we make similar generalization for other three-dimensional shapes?
Well, you see, if you want to change the shape, you have to find the relation between the scattering angle and the impact parameter. So that will be the tough part. How do you, for an arbitrary shape, how do you relate the impact parameter to the scattering angle? Once you can find it, then you're done.
Multiple spheres. Multiple spheres.
Multiple spheres, fine.
And then take out the part that doesn't meet the shape.
What do you mean?
Like you have shine laser, shine a beam, circle, but then cut the parts to make a triangle.
I will not give that as a homework.
Sorry?
I will not even give that as a homework.
Is it doable?
Try it. I mean, if you can do it, I will give you bonus. But 2 spheres is not a bad idea. Let me ask you this question. You have a classical physics. You have a potential well in the sphere. So the potential inside is minus V0, outside is 0. It's not a hard sphere, so if you send any particle in it inside, it will just scatter, and this is your total scattering angle. How do you calculate this angle? Anyway, that is, I might give it as homework. Any other questions on the things that we had done today?
Should we look at the curvature?
You should look at some conservation laws. What are conserved? Is momentum conserved? Do you have translational symmetry?
Not at this point.
Then you don't have conservation of momentum.